Arja Yen, and he's an assistant professor in the College of Computing and Informatics at Drexel University. Arja's research interests involve network science, data science, and informatics in the areas of scientific evaluation, scholarly data mining and analysis, and knowledge diffusion studies. He's published more than 40 papers in venues such as the Journal of the Association for Information Science and Technology, the Journal of Informametrics, and the Information Processing and Management. He won an Early Career Development Award from the Institute of Museum and Library Services in 2015, and a Eugene Garfield Doctoral Dissertation Fellowship from Beta Phi Mu in 2013. And also, and I hope I pronounced this right, Wan Tung Lee Memorial Fellowship in 2011, and a Birnbaum Fellowship in 2010. Finally, Arja is one of our NCDS Data Fellows, and the talk he's giving today will address his Data Fellows research project. The Data Fellows program, if you don't know, is an NCDS program that's open to faculty members at NCDS member institutions, and each fellow receives a year of support from us for work that addresses data science research questions in novel and innovative ways. Today's talk will last about 30 or 40 minutes, and we'll have some time at the end for a Q&A. Feel free to type questions in the chat box as we go along, and we will save those up and hold the questions until the end of the presentation. Thank you so much, and welcome, Arja.
Thank you. Thank you, Karen. Thank you, Stephanie. Let me maximize this screen. Can you hear me fine? Okay. Hello, everyone.
You're good, Arja.
Okay. Hello, everyone. Welcome to this webinar hosted by DataBytes and NCDS Lunchtime Webinar Series. I'm Arja Yan, an assistant professor at Drexel University, Philadelphia, and also an NCDS Data Fellow. It is my great pleasure to talk about my research project here with you. Today, I'd like to discuss my ongoing project on assessing the impact of data and software on science. To begin with, I'd like to talk about my research interests. I study network science, informatics, and scholarly data mining analysis in the area of using scholarly networks to study scholarly communication in the following 4 aspects, as we can see on the slide, including evaluating research impact, studying scientific collaboration, identifying research topics and specialties, and lastly, exploring knowledge flow and transfer patterns. I mainly use 2 types of research instruments. One is network-based, that is, presenting scholarly data in networks and using nodes, links, and their values and attributes to study their characteristics. The other instrument is text-based, namely mining scholarly data using statistical and linguistic methods, such as the example I gave here, which I will elaborate in later slides. I would say that both methods are very popular nowadays, and oftentimes I found the combinational use of both two methods very beneficial. So in my last slide, I mentioned scholarly data, but what are they? Here I gave some examples, such as Web of Science by Thomson Reuters, Scopus by Elsevier, well-known PubMed, and Google Scholar, Zscaler, which is primarily computer science publications, and archive.org, which I think also, in addition to computer science publications, there are also publications on astrophysics, mathematics, and statistics. And DBLP, which is primarily computer science oriented, and Mendeley, I think probably you have downloaded the app on your phone where they will send you update on articles of your interest, and StatuLike, which is sponsored by, also by Elsevier. So this scholar data can be broadly fitted into two categories, bibliographic data and full-text data. Bibliographic data typically contain metadata such as year of publication, title, journal name, author name, affiliations, and cited references, such as the table I gave here. This type of data has been intensively studied in the information science community. Scholars have used this type of data to portray the academic landscape, map the backbone of science, and address questions on disciplinarity and interdisciplinarity. The other type, which is full-text data, a small example here, has become more and more popular in recent years. This type contains bibliographic data, and in addition, also contains everything else in the paper, usually stored in PDF files, text files, or XML files. So since bibliographic data are very useful, why do we need to analyze full texts? I believe there are several considerations. First, full texts contain richer context and content. As mentioned, they not only have bibliographic information, but also the text itself, from terms to sentences to paragraphs to sections, and of course to full text articles. These richer contents grant us to conduct more fine-grained analysis using a large number of research methods rooted in statistics and linguistics. This full text, of course, can be used in conjecture with bibliographic data for more complementary analysis. And I would say that in addition to these reasons, there's also a practicality reason, which is that now we have increased accessibility to this full text, which is not available to us before. And for instance, at least here are some of the open access data corpora, including Core, PubMed. PubMed has a subset called PubMed open access subset where we can download full text for free, and plus corpora, which is also for free, and USPTO, which primarily contains patent publications in full text, and our archive.org, which contains scientific publications in full text. And there are other text corpora that may be freely for academic use. Nature, the esteemed journal, has recently published a news article saying that publishers such as Elsevier has opened their papers to text mining. So in addition, we also have ProQuest and HighTrust and JSTOR. So tons of texts for tons of opportunities. So today, I'd like to show you an example of analyzing full text data. This example applies a bootstrapping method to a full text data of +1 publications and helps address two areas of research that are of interest to me. One is evaluating scientific impact, and the other is examining scientific knowledge diffusion patterns. And I will begin with a description of motivations, and then move to the bootstrapping method, and then to the application of this method to identify software entities in full texts. And then I will present the results on software impact, and the presentation ends with a discussion of future work. As I said, it's a still ongoing project, so there are, I think there are several streams of future work that I believe are very promising. So motivation. So the motivation is primarily predicted upon the changing research landscape. Publications have been long seen as the end research outputs, and this notion has become more transient in recent years, as digital outputs such as software and data can be the end products in many contemporary scientific inquiries. Accordingly, scholars raise the question such as, if I developed a software package, does it count, or how much does it count in my personnel evaluation? So, as an assistant professor, I have this midpoint evaluation, tenure evaluation. So and I think right now our college focus primarily on journal publications and conference publications. But what if I created a software that has been heavily used by the scientific community. So I think they should be counted towards my evaluation. And also questions such as how much contribution have I made when archiving this data set? It relates to the concept that science is itself a self-organizing system. So there is input and there is output. So input is scholars' time and effort, and output traditionally is publications. And now digital outputs such as software and data have become important forms of outputs. So that's our motivation to analyze software impact. So there's the need to initiate impact evaluation for digital outputs, including software and data, to expand the scientific reward system and to develop tools that can identify and characterize software reference contexts in large and heterogeneous full text publications. And full texts are particularly important here because unlike publications, these digital outputs are referenced in unsystematic ways. So I think in the in the future, my goal is to create a way to reference those digital outputs in a consistent way, which is largely lacking nowadays. I think there are some efforts to make the data sets available, and you can assign a DOI to data sets and reference those sets in the same way as publications. But software, I think, is pretty much lacking in its effort. And design hybrid metrics to capture the impact of software in various of scholarly communication channels. So I see hybrid here means that using indicators not just citations, which is the foundation of formal scholarly communication, but the so-called out metrics, such as number of downloads and number of mentions in social media, because digital outputs exert impact in various ways. So that's probably one of the differences of between digital outputs and publications. So today's objective includes first, an introduction of the method to extract software entities from full text corpora. That is the bootstrapping method. I would say that in addition to the bootstrapping method, there are also a slew of other text-based methods that can be used to analyze full text corpora. So the bootstrapping is just one of them. But I think I find this method quite useful for this particular application. And second, an assessment of the popularity of pieces of software in science, so that this type of assessment lies in the very core of my research. And an exploration of software use and citation impact. And lastly, a discussion of disciplinary differences of software use and citation practices. And another stream of my research focuses on disciplinarity issues. So bootstrapping. So what is bootstrapping? Probably you find this term interesting. It is indeed a very interesting method. So namely, bootstrapping is a method that recursively uses seed terms to learn the context, and then uses the context to learn more terms. And these terms become new seed terms. So it's a recursive method. The advantage of this method is that it requires much less hand-labeled data, which is training data, than supervised machine learning methods. So if you have used supervised machine learning methods before, you know that we need to train our data set, at least I would say 20% to 50% of our data set first, before we can use this method to the rest of our data set. So it's a very time-consuming and labor-intensive process. So bootstrapping does not require that. So all we need to do is just to fit this program with a few seed terms, as I will show you an example later on. However, the disadvantage is that the context of the terms to be extracted need to be distinguishable. That is, terms of interest and other terms should pertain to different contexts. So, as I said, software bootstrapping works perfectly for this application because when scholars mention software entities in full-text publications, they mention in a way that is different from when they mention other objects. So that's why we can use this bootstrapping method. So this is a flowchart presentation of the general process of the bootstrapping method. So we first feed this program a small number of seed terms, and for our project, we have 10 seed terms, including some of the most well-known software packages, such as SPSS and MATLAB. And then the program will learn the context of those patterns, and then score those patterns. Here we can set up a threshold and to only use the top performing patterns, and then use those patterns to learn new entities and also score those entities. Again, we can set up a threshold here to only select the top entities, and then using those entities to learn new context that is not known before. And this program, as you can see, is works recursively, and it will stop if this pattern cannot learn any new entities, or if we set up a number of iterations, for instance 5 or 10, and then the program will end. In this case, we let the program run as long as it can extract new entities. I think the program ran around 80 times before it stopped. Our bootstrapping algorithm is regulated by 3 scores, including feature score, pattern score, and entity score. It works well for this particular application. You can and probably need to design your own scoring system to optimize the bootstrapping method. So feature score is a function of 4 elements, including uppercase letter, version number, left trigger, and right trigger. Uppercase letter because we find that most software entities, not all, have an uppercase letter in its entity, such as SPSS or MATLAB. So we gave a higher feature score if this entity has an uppercase letter. The same way for version number. So we will boost the feature score if the context contains a version number. And the context is 5 words with next or previous to the entity. So we will find this 10 words. If you include the entity word, well, that will be 11. So we'll find that will be our context. So we try to find uppercase letters, version number, left trigger, and right trigger within those 11 words. And the left trigger and right trigger is simply a matter of whether those 5 words occur before this seed term or occur after. So a positive trigger word list is formed, which contains 6 terms in total, including package, program, software, toolbox, and toolkit, because we find that when those terms occur, the context is more likely to contain a software entity. Similarly, an active trigger word list was formed, which contains 51 terms in total, such as microscope, scanner, and spectrometer. These terms were obtained heuristically by observing the contexts of software mentions and the context that confuses with software mentions. As we can see, the negative trigger word list contains terms that may be used in the same way as software. So to penalize their occurrence enhances the performance of the method. And I need to say that not all bootstrapping methods use positive and or negative word list. Some only use positive or negative, but not both, and some use neither of them. But we find it necessary in our case because these lists help boost the precision. And as I will introduce to you later, the precision of our method is at the 0.9 level. So next score is called the pattern score. And pattern score and entity score are interconnected. And so, which means that if a pattern extracted more entities with higher entity score, then it is a good pattern. And similarly, and the entity has a higher score if it is extracted by a pattern with a higher score, and at the same time a feature with a higher score. As we can see, pattern score is function of 3 elements: number of positive entities and number of negative entities, and the feature score. And the entity score is a function of 2 elements, including feature score and pattern score. And positive and negative entities are calculated based on entity score. So this bootstrapping method is effective because of those 3 scores, and you can design your own scoring system to fit into your particular purpose. Application. So we made our tools freely available online. It is compiled for the purpose of extracting software entities from texts. So the parameters are set to achieve this goal. So if you intend to work on other entity extraction activities through bootstrapping, then you can try this program out. It's called Stanford Pattern-Based Information Extraction and Diagnostics, which is also freely available online, and it supports a few ways to customize this program to your needs and objective. But if your goal is just to extract software entities, then our program will satisfy this need. And so the data set. So +1 in 2014, there are more than 9,000 full-text papers. And for those full-text papers, there are more than 500,000 sentences and more than 11 million words. So it's indeed a very large data set. And so this figure shows precision and recall. As we can see, so this is our system. In addition, we have 3 baselines. So those baselines are the state of art, and obviously that our method outperforms the 3 baselines. And as we can see, the precision, which is denoted by the y-axis, it's fairly high. So at the beginning, it's almost 100%. Then it just stabilizes at 0.9 level, which means 1 out of 10 words is incorrectly identified, but the majority, all 90% of words are correct. However, if we look at the recall, it's not as high as precision. It stabilizes at 0.45 level. I think this is understandable because software, like other entities, is mentioned unsystematically, and some of the non-typical expressions cannot be effectively captured by this bootstrapping method. And there's always a tension between precision and recall. So if we relax our pattern score, then we may end up in having a higher recall, but at the price of reducing precision. So our argument of choosing a relatively stricter pattern score to ensure precision is that even if some entities were not detected because it is expressed in some irregular ways, they may be mentioned in other, more expected ways, which will be captured by the method in other occasions. So that's our choice. And of course, if your goal is to ensure recall, then you may adjust those 3 pattern scores somehow, and you set up a threshold to enhance recall, but the precision may be reduced. So at the same time, I believe that the customization is vital to ensure performance. So our system outperforms the others simply because that we adopted 4 features: uppercase letter, version number, left trigger, and right trigger. So if you want to use this bootstrapping method, I think it's probably necessary to also include some features that you believe are relevant for this type of application. So I use this slide to show the top scored patterns, and they are lemmatized. So you can see, instead of saying is, we use be. So that's simply a linguistic approach. And so the top one is use software. So use SPSS software or use SAS software. So this is the most used pattern to express software use. And we can see perform use, be perform use, analyze, be perform use. So those are the most effective patterns that extracted the highest number of software entities. So using this method, we apply it to the +1 corpus, which contain more than 9,000 full-text publications. So this is the result. Here we show the most used software. This is rank, the software name, number of mentions in among the 9,000 publications. Free here means if it is free for academic use. As we can see, statistical software entities such as SPSS, SAS, and Stata, MATLAB, even Excel, and some of those are packages. So R is not. I think when I first present this table, the many scholars ask me, so where is R? So R, I think, exists. It's just instead of having R, we have many of the R packages, which is presented here. They are very popular in the scientific community. So now, but we can see probably around half of them are free for academic use, whereas the rest half is not. If we move to the most cited software, we can see majority of them, I think for the top 20, there's only one SS2, so there are only 3, yeah. There are only 3 that are not free, whereas the rest are free. And here, MAGA is the abbreviation for molecular evolutionary genetics analysis. And so it's a bioinformatical software package. And BLAST is for basic local alignment search. 2, which is algorithm for comparing primary biological sequence information. ImageJ, as the name tells, is the information processing and analysis in Java. And MASO is for multiple alignment software. So we can see some of the bioinformatics packages are highly cited in the community. And there's if we compare the number of mentions and number of citations, we can see there's a correlation between the two, and the correlation coefficient, this is by Spearman, which is 0.62, so it's a strong or evident correlation. I use this slide to represent the popularity of software. As we can see, more than 90%, close to 80% of articles mentioned software, and for those 8,000 or so articles, Altogether, we identified 2,369 unique software entities, which resulted in more than 43,000 mentions and more than 4,000 citations. And top 20% most frequently mentioned software entities attracted more than 80% of mentions, which is expected because we all know this 20-80 rule. 20% of the wealthiest people have the wealth up to 80%, which now is maybe even more. The discrepancy may be severe. Or we can say top 20% of articles resulted in more than 80% of total citations. So this is parallel distribution. At the same time, 40% of software entities did not receive any citation, and almost 50% received less than 3 citations. So this may coincide the concept of obliteration by incorporation, which means that people no longer said things like Earth is a planet in the solar system because it has been well acknowledged. It's now really expected for you to cite SPSS when you write a paper. But I think for the free software entities, particularly those developed as a result of funded research project, there is a need to reference and acknowledge them in a more consistent way. So this is our assumption. So now we move on to the disciplinary comparisons. Here we show the proportions of papers that use software across in total 12 disciplines. As we can see, the highest is agriculture, which resulted in more than 85% of these publications mentioned software at least once. The lowest is mathematics, which is 61%. As we can see, biology, chemistry, they are all above 70%. So software entities, software packages are widely used across nearly every scientific discipline. We use this slide to compare number of mentions and number of citations for each of those 12 disciplines. The highest, again, is agriculture, which has average mention per article is 4, and the mean citation per article is 1.5 for software entities. So as we can see, there's a difference between the average mention per article and average citation per article, which again I think it's expected because people no longer cite SPSS or MATLAB when they use them. But again, I think it's important for us to cite those free software packages that are developed because of a funded research project. Because I think it's important for the funding agency and also the scholar, the developers themselves, to know the impact of their research, not just in the form of publications, but also in the form of digital outputs such as software. I call this extensive rich because here we show the number of disciplines and here the number of software packages. As we can see, majority of software entities have been used in 2 disciplines, and a small number have been used across all 12 disciplines. So they are definitely the most extensive ones here. And here we show the top 5 most mentioned software for each of those 12 disciplines. As we can see, SPSS and MATLAB and SAS, ImageJ, and Stata, and those software packages, they are heavily represented in this table. If we move on to the most cited software entities, we can see some disciplinary differences occur here. Again, it's for molecular evolutionary genetics analysis, and BLAST is also for bioinformatics analysis. And wagon here, let me see, it's a community ecology package in R, so it's for ecology, which is very appropriate here. And the VMD here is for visual molecular dynamics, which I think is heavily used in physics, at least according to our data set. At the same time, I need to mention that in +1, sometimes one paper is assigned to more than one discipline, so that's why there might be some crossover here. So now, I think, yeah, I'd like to move on to the future work. So tons of opportunities ahead of us, so this is just the beginning. In our future work, both reference and usage-based metrics will be designed because while citations form the foundation of formal scholarly communication, software and data have exerted heavy impact when scholars access, use, or adopt them in various scientific inquiries. Therefore, hybrid metrics are indispensable for assessing both formal and informal impact of software and data. So as we can see here, reference-based metrics will include number of citations, and usage-based metrics will include number of mentions in full-text publications, number of downloads. I think that's also a very important indicator, particularly for software. So if the software has been downloaded thousands or tens of thousands of times, then it must be a very popular one, and the developer should be acknowledged. Number of visits, that's also a strong indicator of popularity. And number of discussions in social media. So it's another way of measuring the impact. Additionally, we can develop a web plugin to include a layer that allows the plugin to exchange data with existing publication-driven impact tools, such as impactstory.org and altmetrics.com. So I think there are already some examples that publishers incorporated those altmetrics indicators in assessing their publication's impact. As we can see, I think if it's like for impact story, there's like a rainbow sign of some kind showing the impact. So this has been downloaded 20 times, cited 5 times, and has been discussed in social media 3 times. So those can all be used to assess the impact. A plugin will be designed as an open source tool that gathers the real-time software and data metrics from weblogs, such as and also Google Scholar and some APIs. Mendeley, Facebook, such like, they all provide such APIs that allow scholars to extrapolate data. And software developers and data producers can add those plugins to their product websites to allow for more transparent impact assessment. As I said, not only publishers have done that, the developers themselves can also use those plugins to present the impact of their research. And lastly, attribution and scientific rewards, different roles and software developers fulfill, because nowadays I think the concept of authorship has become interesting, more and more interesting, because I think some journals, they have very strict rule on what on who can serve as an author. If I just provided a proofreading service, then definitely this proofreader should not be listed as an author. But I think for digital outputs, such as software and data sets, it's important to establish some kind of attribution system, because I think the roles of software developers fulfill can be more ambiguous than publications or other similar research projects. I think those questions should be clarified in probably from in the very beginning. And so we mainly talked about software entities. So our next step also includes the identification of how data sets have been mentioned and used in scientific research. So those are some of our ideas. For instance, we will design case studies to examine their provenance. I think the concept of provenance is important. So where is this data set from? So does it have a DOI? Does it have a URL? Or is it archived in institutional repositories? Or is it archived in some journal-specific repositories, such as Dryad, right? And if it's just stored in some private archives. Now we can also cross-reference with citation data from data citation index by Thomson Reuters. And also we can triangulate data impact by using usage, mention, and citation statistics in the same way as our software entity assessment framework. And lastly, we can involve time as another dimension to conduct trend analysis and predictions. So I think this is, I found it very interesting to add time as a dimension for nearly any type of research I'm doing nowadays, because numbers alone don't tell a very good story. For instance, this data set or this software entity has been cited by 50 times in 2015, but what does it mean? Is it good or not good? But if we can draw a timeline and see how this product has been cited in the past 5 years, then we can definitely tell a very coherent and vivid story. So that's all for my presentation today, and we appreciate the generous support from NCDS. And if you have any questions, please let me know. Thank you.
Thank you, Arja, for that really interesting talk. If anyone has any questions, feel free to submit them right now. Now is your chance. So we do have one question here. I'm going to read this.
Sure.
Okay. What is the estimated date of availability for the web page plugins to capture citation and altmetric impact data?
That's a very good question. I think scholars and publishers just got started to make those data available. And previously, we don't really know the download information, like such as how many times this paper has been downloaded. But I think last time I checked Wiley.com, and it is available, which is quite interesting to me to say that. I think this is a trend. Transparency in science has been demanded for quite a while, and I think what I'm doing, this research project is just probably one of the many efforts in the open data or open data, open science movement. And I think I can already estimate the percentage. I think there are some studies on that to see how many times. Sorry about that. How many times the percentage of data set availability. But I think it probably is not very high, as at least we can see for software entities. Not all of them are free available for academic use, but I think, as I said, should be a future trend that developers and data archivers will make an effort to make their data available.
Okay. Okay. So next question that we have here is, how did you select the 9,000 PLOS One papers out of the approximately 30,000 that they published in 2014?
I think probably they published 10,000 around 10,000 publications in 2014. I could be wrong. Oh yes, that's a good question. And now I recall some details. Is that we select those articles that have a method section. So our bootstrapping method was applied only to the method to those publications that have a method section. So a lot of articles that does not have this section were screened out. And also because we want to do cross-reference with disciplines and found some disciplinary patterns of software use and citations. So we also screen out those publications that have not been assigned with a discipline. So I think by doing those two filtering process, then we ended up in having around 9,000 publications. But yeah, definitely you can apply the bootstrapping method to all 20,000 or so publications in +1 in a year, and without doing any filtering work. You can also not only apply this method to the method section, you can apply it to the introduction, the discussion, the result sections, or even every section in the paper. We did it because again, after some initial work, we found that most software entities are mentioned in the method section. So to save some computational to reduce the computational complexity, as we can see there are more than 11 million words just for the method section of those 9,000 publications. So we decided to only focus on that section instead.
Okay, and we have a couple more questions here. I'm just going to take them in order. Next one is, you said you'd be interested in more standardized mechanisms for citing software. Are you aware of efforts in this space such as the Force 11 Software Citation Working Group? And then there's the URL that's at github.com. And Arja, if you want that URL, we'll make sure you have it. But it appears this is a working group that's on github.com.
Great, excellent. Yeah, I will definitely be interested to know about this working group.
Okay. Then the next question is, how would you include software in a broader sense in your analysis, like codes, scripts scientists write, for example? They usually do not have name and maybe are called something very general, like Python scripts.
Yes, that's a good question because again, this is fairly new, and we have to figure out a lot of things for ourselves. And so, if you refer to this paper published in Journal of Informatics, we mentioned our standard of. So we gave an operational definition of software. So what is software? And we like Python or particular programming language like Perl or Java, we exclude them. So we believe it's not a software. We also exclude operational operating systems like Yosemite by Apple, things like that. And also a particular algorithm, for instance, the maximum spanning tree or minimum spanning tree, those kind of algorithms, we believe that's just a method or an algorithm, not a software. So software has to be more tangible than just some lines of code. So yeah, we did do some definition of what can be extracted in full-text publications. But yes, I definitely see the potential of expanding this concept and probably extract more things, not just software entities, but as you said, theories or methods or algorithms, so on and so forth. Thank you.
Okay, great. Any other questions at this time? Going once. Oh, looks like we have one. Okay. Next, another question is, will there be a formal method of making sure software is discovered by your system with explicitly provided metadata?
That's a very good comment. Yes, I think there should be a way, and I think a simple way will be just adding a tag to it, right? You can just add tag SPSS, software SPSS and that tag. So we can just add a tag to denote that's software, by adding this type of metadata. Yes, I definitely think there should be a way to do that. But then, in addition to that, you can also tag other things, as I mentioned, like algorithms, methods, series, location, people, scholar, reference, tons of opportunities. Yeah, this annotation, I think, will provide a lot of ways for readers and also scholars to make a more effective communication. And I think there are efforts in the bioinformatics community where they will tag like things like disease, drug, compound, gene, things like that. I think to make their to make a more easy readership. I think, but for other areas, probably because there's a lack of good controlled vocabulary compared with the biomedical community. So this effort is not really being achieved yet, but I think yeah, in the future there should be such a way to make our reading papers easily. Yep.
Okay. Any other questions at this time? I'll do it one more time, going once, going twice. Okay, I think that wraps it up for today then. And Arja, thank you very much for presenting today's webinar. We really appreciate your time as well as the time of all our attendees. For those of you in the audience, remember we do the DataBytes lunchtime webinar series monthly, generally on the first Wednesday of the month. We're going to take a break in December. But we will be back on January 6th for another webinar, and we'll be sending out some information on that shortly, so look for that. We hope to see you or hear you or at least have your virtual presence at that time. Thank you again, and thank you, Arja, and everybody have a good day and the rest of the week, too. Thanks.
Great pleasure. Thank you.
Thank you.
Bye.
Bye-bye.